Okay, so hello everyone. I am Aniruddha and today we are meeting for the sixth time in this course on measure theory from NPTEL. So we have completed half of the course and another 6 weeks of this course are remaining. So till now, let me just recall what all things we have done and then I will give a window to ask questions. So we started with some collection of subsets of a given set X. Then we classified them as semi-algebra, algebra, and sigma algebras. And another class of sets we saw was the monotone class. Next, we saw the length function and whether this can be extended to something more. Extension of this length function to a larger class, whether this was possible or not. This gives rise to the notion of measure spaces, or first measurable spaces and then measure spaces. Next, we saw what is called as Lebesgue measurability in R. Measurability of subsets of R. So that was through the outer measure. And in this week, we saw what are measurable functions. On a measurable space and on a measure space. And of course, the lectures followed the properties of these measurable functions. Basically, we saw the algebra of measurable functions, that addition of two measurable functions is measurable, the scaling of a measurable function is measurable, the absolute value of a measurable function is measurable, and so on. I would like to point out here that the most important part in this measurable function is the simple functions, simple measurable functions, and how a non-negative function can be approximated using non-negative simple measurable functions. Using non-negative simple measurable functions. So all these things we saw during the lectures. Now, if anybody has any doubts, they can ask. So also the online YouTube audience, if they have any doubts, they can post it on the chat. There might be some latency. I actually forgot to change the settings. So you might get a 60-second delay in whatever I'm seeing. So I'll give you 1 minute. If you have any questions, you can post it in the chat on YouTube. And those who are attending in person through the Google Meet, they can unmute and ask. Okay, so I think there are no questions. Jitesh, do you have any questions?
No, sir. Not right now.
Okay. So today what we are going to do is we are going to look at some results from analysis that usually help us in solving the problems. And there was a demand of solving assignment number 5. So I will try to solve the questions of assignment 5 today. So I hope that everyone has done assignment 5, and I think it has already been graded. So now you cannot change the answers. So let us start with a very basic thing. The first result in today's direction. It says that every open set in R is a disjoint countable union of open intervals. Should write this union of all those R positive such that x minus R to x plus R is contained in U, x minus R to x plus R. So what I am doing is, see, this Rx could be really small. For instance, this could be our U, say 0 to 1 is our U, and x could be here. Now this Rx could be this one, right? So this is x minus Rx, x plus Rx. But a bigger thing can also work. Say x plus Rx prime, this is x minus Rx prime, and this is x plus Rx prime, and then so on. So what I am saying is, look at the largest possible interval with center x, and move R towards left and R towards right. So whatever is the largest possible interval, such that it is still contained in U. So notice that Jx is still inside U, and Jx is an open interval. Okay. Now, so surely x is inside Jx for each x. This implies U itself is actually a union of x in U, Jx. Do you agree with this?
Yes, sir.
Okay. But now see, let us look at this figure itself. Okay. Maybe I should not define Jx this way, because this is might cause a problem. Not always the midpoint we want. So Jx is the union of all those intervals I, such that x is in I is in U, and I is an open interval. So I am allowing the asymmetric intervals as well. So something like this is also true. So from here to here, this is our I. Okay, so let us see what can happen. Again, let us look at this 0, 1. Maybe I'll draw a bigger diagram to make it visible. Initially, I took this point x. Now, something like this I was possible. This whole thing was I. And even the symmetric intervals are also, one of the intervals that we are taking. But what happens if I take another point? Say I take y. Then again, I can look at this interval, right? From here to here. This contains y, but this also contains x. So, do you observe something from this diagram? Yeah.
Yes, sir. So there may be some intersection between these sets.
Correct. So, see, the intersection is actually what is happening. The largest interval containing x and the largest interval containing y, they are the same, at least in this case, right?
Yes, sir.
Because in both the cases, it is interval 0, 1. Now, what I will do, let us define a relation on U as follows. So, x is related to y if and only if Jx is equal to J1. So, now I will ask 3 questions. Please quickly tell me the answers to this. First question, is this relation reflexive?
Yes, sir.
Yes, because Jx is equal to Jx for any x, so x is related to x. is this relation symmetric?
Yes, sir.
Right? If Jx equal to Jy, then Jy equal to Jx. So x related to y implies y related to x. And is this relation transitive?
Yes, sir.
Yes, because Jx is equal to Jy and Jy is equal to Jz. It implies Jx is equal to Jz, so that x related to y and y related to x together imply x related to z. So, did I say y related to x? I meant to say y related to z. Okay. So, all these answers to this question is yes. And what does this imply together?
That this is a equivalence relation.
Right. So, this is an equivalence relation. Okay. Now, once you have an equivalence relation, the question is what are the equivalence classes, right? So, the fourth question that comes is what are the equivalence classes of this relation? Equivalence classes of this tilde. So, what do you think? What are going to be the equivalence classes of this?
Sir, in this particular example, it seems like there is just one equivalence class.
Correct. So, and why is that true? Like, because you cannot have another interval bigger than 0, 1, right?
Yeah.
Yeah. So, here, if you look at this definition of the relation, what it says is two points are related if and only if the largest interval containing those 2 points are same. So, isn't it the case that these are the equivalence classes? So, the equivalence class of x is defined as all those y in U such that y is related to x, which is same as all those y in U such that jy is equal to jx. But can we say that this is equal to jx?
Yes, sir.
Right? So basically all these jx's that I have found, that is the largest interval containing x and contained in U, where I have written, yeah. So this jx here. This is an equivalence class, which means either they are same or they are disjoint. Therefore, for each xy in U, either jx intersection jy is empty or jx is equal to jy. They cannot have a non-empty intersection unless they are equal, right? Yeah.
Yes, sir.
Okay. Okay. So, therefore, now see what I will do. I will maybe I'll write it again. No issues. So, U I had already written as union of x in U jx, but here there are many repetitions. So, I will write this as union of I in I ji, where ji's are the equivalence classes. Equivalence classes, that is ji is equal to jx for some x. I am not saying for a unique x. Ji is equal to jx and ji intersection jk is empty for I not equal to k. And this capital I is some index set that we have to study. Some index set that we need to study. Okay. So, okay, is this clear? Now we have written U as a disjoint union of open intervals.
Sir, this analysis is valid only for metrics defined on Rn.
Let us not go into that. This is valid only for R for the time being.
All right. Yes, sir.
Yeah. But whatever you are saying is true because there we can sort of separate it into balls and then union of balls, right? Is that what you want to say?
Yes, sir. Because I've seen a similar proof for R3. They had
Uh,
used cubes to show the same thing. But now I was wondering if we could extend this thing to arbitrary metric spaces.
yes, yes, we can. No, not yeah. We can extend this thing to arbitrary metric spaces. We can write a open set as a disjoint union of balls or disjoint union of some nice open sets. But then whether that disjoint union is countable or not, that is a very particular case in R and Rns.
Yes, sir, you were inaudible. Sorry.
Oh, I was inaudible. See, what I am saying is up till this step, whatever I have done, that we can do in any metric space. Because I have not
Yes.
used any property of R here, right? I have actually used the property that this intervals basically they are open balls,
Yeah.
right? So up till here, everything is fine. You can just extract this proof and just carry it on to any arbitrary metric space. But now the next question is whether this, see what I am saying is it is a countable disjoint union, disjoint countable union of open intervals, right? So I still have to prove that this index set I is countable.
Yeah, we have to. Yeah.
And that is true only in the case of Rns. That is not true in arbitrary metric space.
Yes.
Yeah. So, so let us prove that this I is countable. So do you have any idea how to prove it? I have given you a hint that something special about R we are going to use.
A sigma finite property we had used when in measure theory. Something similar, sir.
But we don't require that much. Just some special property of R, the real numbers.
Oh.
See, can I say that each Ji contains one rational number?
Oh, yes, sir.
Can we say that? Yeah.
Yes, sir.
So for every I, there is a rational number in Ji, right? And what we have is if I is not equal to J, Ri cannot be equal to Rj because Ji and J, I mean Ji and Jj are distinct. They are rather disjoint. So therefore, from here we can define a function C from I to Q as C of any interval Ji is this Ri. And what can you say about this function? Is this 1 1?
Yes, sir.
1 1, right? So then, since this is 1 1, from here I can say that I is countable. Right? Because then I cannot have more elements than rational numbers, and rational numbers have countably many elements, so I has countably many elements. So this implies that U is a disjoint countable union of open intervals. Okay. So this is one of the properties that I feel it is very important in measure theory because a lot of times using to get Lebesgue measurable sets or something we use open sets, and then open sets can be written as a disjoint countable union of open intervals, and the measuring the lengths of intervals is very easy, right? That is just the difference of the endpoints. Okay. So this is one thing. So do you have any doubts here? Let me ask the YouTube audience as well. Yeah, Jitesh, do you have any doubts?
Yes, sir. So over here, the open intervals that we get, countably many, those are finite for us, or they could be in like.
No, no, no. They may not be finite.
Oh,
See, for example, just look at R.
yes, sir. And the open set will be. Yes, sir. Correct.
This is not a finite interval, but it is an open set.
Yes, sir.
Okay. Or okay, let me just quickly give an exercise. This you can try very easily. In arbitrary metric spaces, okay, every open set is a disjoint union of open sets, or rather open balls, but it may not be a countable union of the union may not be countable. So you try this. If you have any doubts, you can mail me, or we'll discuss it next time. Not very difficult.
Yes, sir.
Let us move on. Let us look at one more result. So this result is about, well, yeah, or perhaps let me not call it as a theorem. Uh, okay, maybe we can call it as a theorem because it doesn't really depend on this one. So the result says that we cannot have an uncountable family of disjoint open intervals in R. Okay. So what does this mean? It means that if F is a family of I such that I is an open interval and I intersection J is empty for I not equal to J, then F is countable. So let us, can you quickly tell me a proof of this thing?
So, yeah, if we can show this by contradiction.
Yeah, but can you quickly construct the proof?
Yes, sir. So let us assume that we have an uncountable family of disjoint open intervals
Okay,
in R.
F is uncountable.
So each
Mhm.
element of F will contain one rational number.
Exactly. So for each I in F, there is some Ri in I intersection Q, right? Then,
So that so that will essentially entail that there will be uncountably many rational numbers.
exactly.
Because yeah,
Or yeah, or in other words, we can define a map C from this F to Q as C of I goes to Ri. But this is a one-one map, which implies F is countable. So actually, we don't really require this assumption that F is uncountable. The proof is just these two lines, right?
yes, sir.
Okay. So these are two results that will be helpful at some point, and I know that they are helpful at least in assignment 5, which is why I have discussed them here. Now, let us look at a property of outer measures. So we have already seen the translation invariance, right? We have seen that the outer measure lambda star is translation invariant. Correct?
Sir, the outer measure on the
Yeah, yeah, yeah.
length function.
Yes, yes. Outer measure of the length function. Actually, from here only we got that the Lebesgue measure is translation invariant, right?
Yes.
Okay. Now the question happens that what about scaling? What happens to lambda star under scaling offsets? That is, suppose that E is a subset of R and C is for the time being, let us assume it is a positive constant. Do we have any connection between lambda star CE and C times lambda star E? Whether they are equal or what happens, right? One might expect that this is true, because if E is an interval, if I scale that interval, then the length is going to be scaled with the same factor, right?
Yes, sir.
So let us see. So first, that is what I am going to prove. Let I be an interval. If lambda star I mean, okay, since it is an interval, I can write lambda. So if I is infinite, then this lambda star I is plus infinity. And in fact, Ci is also infinite, since C is positive, right?
Yes, sir.
So lambda star Ci is plus infinity, which is C times lambda star I. So this is a very trivial case where we don't have to do anything. So let us assume that I is not infinite. So I is finite. That is lambda star I. That is the length of I. This is finite. And then we have to check whether the length of Ci is same as C times length of I. So, without loss of generality, since I is finite, I can assume that I is of this form, AB, for some AB. Correct? Because nonetheless, even if it is open somewhere and left open, right closed, or right open, left closed, and all those things, the length is still B minus A. So, what can we say about Ci? What type of set will Ci be?
It will be the interval CA, comma CB.
Correct. It is Ca, comma Cb. So, what is length of Ci? This is Cb minus Ca, which is C times length of I. Correct?
Yes, sir.
So at least whatever we expect, it is true when I is an interval. Now let us take arbitrary sets and let us see whether this happens or not. No, sorry. Yeah. So let E be a set. Then, lambda star of E is the infimum of something. Right? That's something I leave it to you to write it down. But since it is the infimum of something, I can say that for each n, there is a sequence ijn of intervals such that this E is contained in the union of this sequence, but union taken over J. And if I take this sum, J equal to 1 to infinity, lambda of ijn's, this is strictly less than lambda star E plus epsilon. Oh, sorry, I have taken n, so maybe I should write 1 over, right?
Yes, sir.
This is the definition of infimum. So now you see, what do we want? Yeah, we want C times A, right? So what can we say about C times E? Can I say that C times E is contained in C times union J equal to 1 to infinity Ijn, which is actually equal to J equal to 1 to infinity C times Ijn, or at least contained in. Can I say this?
Yes, sir.
So now see, if this is true, then by definition, lambda star of C times E must be less than or equal to this sum, J from 1 to infinity, lambda of C times Ijn, right? But
Yes.
this is same as C times summation J from 1 to infinity, lambda of Ijn's, which is further strictly less than C times lambda star E plus C by N, correct?
Yeah. Yes, sir.
And this is true for each n. Therefore, lambda star CE is less than or equal to C times lambda star E. Now from here, can we quickly say that like this directly implies lambda star CE is equal to C times lambda star E. Can we directly say this?
No, sir.
No. See, think about it. I mean, directly in the sense, something very trivial calculation which does not require other analysis.
Oh,
See, notice that C is positive. So if I can multiply, I can also divide, and it will not change anything, right?
yes, sir. Yes.
Now, all these calculations are going to be the same. So what happens is lambda star of E, I can write lambda star of 1 over C times CE. But then from these calculations, this is less than or equal to 1 over C times lambda star CE. Or what is the same? C times lambda star E. This is less than or equal to lambda star CE. Right? And this would immediately give us this.
Yes, sir.
So at least when C is positive, we have that lambda star CE is equal to C times lambda star E. What happens if C is negative?
Sir, I had a doubt.
Yes.
So, using the example for a finite interval, we already had that lambda of CE. So, okay, okay. So, I'll rethink about it. Sorry.
No, no, you ask me. Perhaps someone else
Uh,
might have the same doubt, right?
yes. So, exactly. So, lambda, if I have the interval a comma b, then lambda of I. So, lambda of ci is equal to c into lambda of I. So, this
Correct.
is okay. This is the exact result that we obtained. Yes. Sir.
Right.
I thought that we'd expect some inequality.
No. Why would we expect some inequality here? See, this is natural, right? If I have an interval, if I scale it, then the length is going to be scaled by the same factor, right?
Yeah. Yes. Sir.
Okay. So now the question is, what if C is negative? So what do you think? What should happen if C is negative?
So, um, the sign might not, the length might not change for a finite interval.
Length might not change.
Using the example of a finite interval, you see that it just reflected about the origin, the interval. So the length is still the same.
Correct. But yeah, so length is, I mean, C is not minus 1. C is negative anything. Whatever you said is true for when C is minus 1, right?
Yes, sir.
So the first observation is that if C is minus 1, then the length does not change. So that means lambda star of minus E is equal to lambda star of E. And again, why is this true? This is true for intervals because again take two cases when interval is infinite, then minus of that interval is also infinite. In that case, both the things are plus infinity. And when it is finite, we are just flipping the interval. So a comma b becomes minus b comma minus a. So again, that length becomes minus a minus minus b, which is b minus a. So this is true for intervals. Did I go too fast?
No, sir.
So now let us see what happens for arbitrary sets. So again, lambda star minus e is the infimum of something, which means for each n, there is a sequence ij of intervals with this minus e is contained in this union inj's, and the sum lambda of inj's, this is strictly less than lambda star of minus e plus 1 over n. And then use the similar argument to get that this sum j equal to, or rather Oh, sorry. Here I should write E. Right? Here it should be E. So lambda star of E minus E. This is less than or equal to summation j from 1 to infinity. Lambda of minus I and j's, which is same as sum from 1 to infinity lambda of I and j's, which is strictly less than lambda star of E. Yeah, again, this is not minus, this is plus. Lambda star E plus 1 by n. And this is true for each n, implies lambda star of minus E is equal to lambda star of E. Sorry, this is less than or equal to first, but then lambda star of E is what? It is lambda star of minus E, which is further less than or equal to lambda star of minus E. And together they give us lambda star of minus E is same as lambda star of E. Is it clear?
Yes.
Now if C is negative, then minus C is positive, and hence lambda star of C times C, this I can write because of this equality of this, minor multiplication by minus 1 does not change the outer measure. So it is lambda star of minus C times C, which is minus C times lambda star E. But I can, to avoid the writing this negative sign, let me write is mod C times lambda star E. Okay.
Yes, sir.
So essentially we have proved this result. So I have proved it for outer measure, but let us rather prove, or maybe I'll write the statement for outer measure only. Okay. For any E in R and C again in R, lambda star of CE is equal to mod C times lambda star of E. So looking at this analysis which I have done, one may ask that I have missed C equal to 0 case. But C equal to 0 case is trivial because in that case C times C is singleton 0, which has outer measure 0, and mod C is 0, so mod C times anything is again 0. So that case is not really missed, it is trivial, and I have therefore not included it here. Okay, is it fine, or do you want to ask any questions?
Yes, sir. This is fine.
Okay. So, there are a few corollaries to this result. So maybe I will just write the statements. I will not write how they are proved. The proof is very easy. So the first corollary says that you take any epsilon positive, you can always find a subset which is not measurable, such that A is not measurable. And the outer measure of A is less than epsilon. Corollary 2 says that for every M positive, you can find a non-measurable set. So all this is same. And the outer measure of A is bigger than M. So you can find a very small non-measurable set. You can find a very large non-measurable set. In fact, for every M positive, you can find a non-measurable set with measure exactly equal to M. So I'll give you a hint, and perhaps you can tell me how do we get this set A. So we have already seen a non-measurable set with finite outer measure. So you use this and tell me the proof to any one of these. So just call this set V for the time being. This V stands for Vitali set. I don't know if the name was given in the lectures. Yeah. So could you quickly use this hint and tell me the proof to any one of the corollary? The other two will follow in a similar way.
Yes, sir. So if we have V which is non-measurable, then
Right.
lambda star of V is already defined. Then
Correct. It is finite, right? That is
Yeah.
what we have proved.
Yes, sir. So we just use the theorem that we just proved and use for a given m greater than 0, we
Correct?
choose C is equal to m by lambda star of V.
Exactly.
Thus that we get the result.
Exactly. Exactly. So what we do, what we do is choose C as m by lambda star V, then lambda star of C times V. Now this is positive. Notice that lambda star V is positive, m is positive, so this is positive. So this is C times lambda star V, which is m. If you want bigger than m, choose this to be 2m. If you want less than epsilon, choose this to be epsilon by 2. And then, you can get all these three corollaries. Okay. So I think, yeah, these are all the things that I wanted to discuss. Now let us look at assignment 5. So have you completed assignment 5?
Yes, sir.
Okay.
So,
So, yeah, tell me.
sir, I had a doubt regarding non-measurable sets. So,
Uh-huh.
when we are talking about the extension of the length function to lambda star, then there exists some sigma algebra S star such that over this sigma algebra, the outer measure is countably additive. And
Yes,
so non-measurability would mean that if you have some subset of R which does not belong to that sigma algebra S star, then one can directly say that that subset is not measurable. Is that correct, sir?
correct. Yeah,
I just wanted to confirm this
yeah, yeah,
particular
yeah.
thing.
So, do you remember how we define this extension? So, let me just go through that once again for other viewers as well. So, we had a collection C, usually an algebra, and here we had some notion of measure. That means we had a finitely additive, or in fact, a countably additive set function with the property that the value of the empty set was 0. From here, we went on to Tx and lambda star, where this is the power set of x, and this we called it to be outer measure. And using some condition, so measurability conditions, they are usually called as the Carathéodory conditions. Anyway, this name is not important. Nobody is going to ask you what it is called, but still, yeah, using some measurability conditions, we reached to a sigma algebra and the measure lambda. This is sigma algebra and this is the measure. And this sigma algebra particularly, we called this as the space of measurable sets. So anything which is not here is not measurable. So is it clear?
Yes, sir. Yeah.
Any other questions?
No, sir.
So let us discuss assignment 5. Somebody had asked in the mail, but I don't think they have joined today. But nonetheless, let us discuss the solutions at least to some questions. So the first question asks that suppose that IU is the algebra generated by no, sorry, IO is just the collection of all open intervals. Collection of all open intervals, and ICO is the collection of all left closed right open intervals. The question asked whether the algebra generated by IO is same as algebra generated by ICO. So what do you think? Are they the same?
No, sir.
No. Why?
I don't really know about that, sir.
I couldn't hear you. Could you repeat, Jitesh? I think he lost the network. So see, these are not equal in general. And why is that so? Because if I take a finite union of these type of elements, ai comma bi, I equal to 1 to say n, then we cannot get open on the left hand side. This is not open on the left side. Because what we are essentially doing is this. Say A1, B1, A2, B2, A3, B3, and perhaps A4, B4. If I take the union, then what is going to happen? This is A1 and this is the final interval, right? This is union of
Yes.
AI, BIs. And this is not open on the left. In fact, one can prove why is it not open on the left. So I will leave that to you. That is because the minimum of AIs, I from 1 to n, of course, this is not an interior point. Because for otherwise, if it was interior point, it was a minimum, right? So there would be a open interval inside the left closed interval. That is not possible. So do you understand this?
Yes, sir. Initially, I had thought that we had a sigma algebra, then it would have been possible. But for
Yes.
finite unions, it is not possible.
Exactly. For finite unions, this is not possible, right? So let us look at the second question. The second question asks whether a countable infinite set is a null set. So let A be a countable infinite set. So what do you think? Is it a null set?
Yes, sir.
Why?
So if we can just show that the set of all rational numbers is a null set, then any countably infinite set could be a subset of it or map to a subset of it.
Okay, what about this set? Say you take A to be root 2 to the power n as n varies over z. Is this a countable infinite set? Yes? Hello?
Uh, Set of rational numbers.
No, I couldn't understand.
So logic doesn't work because this is clearly not a subset of the set of rational numbers. So
Exactly, but this is not contained in this set of rationals. Right? This is a countable infinite set, but it is not contained in the set of rational numbers. So it is not enough to prove that the rationals are null set. What is enough to prove is the singleton sets are null sets. So do we know that singleton X is a null set? I cannot hear you. Could you repeat?
yes, sir. I think my net got disconnected. Yes, a singleton set is a null set.
Why? Because it is a interval, right? This is interval x comma x, closed interval x comma x, and the length of this is 0. So this is a null set. Now A is countably infinite, so I can enumerate it x1, x2, and so on. So basically, I can write it as a union of 1 to infinity xn's, and this is a disjoint union. Okay. What about lambda star A? Lambda star A is less than or equal to 1 to infinity xn's, right? Lambda of xn's, which is 0. Is that right?
Yes, sir.
But then this is anyway bigger than equal to 0 by definition. Therefore, lambda star A is 0, which implies A is a null set. Correct? Yeah, is this fine?
Yes, sir.
Okay. Let us look at question 3.
Am I audible?
So, yes, you are audible. So, the question 3 asks, if A is a subset of R, it is a null set. This implies that there is a delta positive and, rather A and delta positive. Uh, no, A need not be positive, right? A is contained in R and delta is positive, such that A minus delta to A plus delta, this is contained in A. Is this true or not? So what do you think? Is this true?
No, sir.
Why?
So if you already have a subset which has a grade, which has a measure greater than zero, then by
Right.
monotonicity property, the superset will also have a greater measure.
Exactly.
So it's not
So
a null
lambda
set.
star is monotonic. So it is lambda star A minus delta A plus delta is less than or equal to lambda star A. But this is 2 delta. And on the right hand side, we have 0, which is not possible, which is a contradiction. So, okay, so third one is false. What about the fourth? What does the fourth one ask? Yeah. So fourth one asks whether any union of null sets is a null set. So again, what do you think? Sorry. Is this statement true?
Uh, so if you can take uncountable union of all elements of the set R, then it's
Yes,
clearly not a null set.
exactly. So R is a union of null sets because it is a union of singleton sets, but this is not a null. Okay. So the fifth one may be a bit difficult, right? That if E has finitely many limit points, finitely many limit points, then E is a null set. So is this true? Have you solved it?
No, sir, I couldn't solve this one.
Okay. So let us see. So my first claim is that if E has finitely many limit points, then E must be countable. If E has finitely many limit points, then E is countable. So why is that true? Because let us see, there are finitely many, so let us enumerate it. X1 to xn, or perhaps xm. Let these be the limit points of E. Okay. Then E tilde, if I just remove all these points from E, x1 to xn, this has no limit point. Right? Hello?
Yes, sir.
Yeah. But if it has no limit points, it means what? This means you take any x in E tilde, we can find a delta x such that x minus delta x to x plus delta x, this is like with intersection with E tilde, this is just singleton X, right?
Yes, sir.
Okay. So now from here, it is going to be very easy. Why? Because let us define En as follows. Look at all those X such that X minus 1 by N to X plus 1 by N intersection with E tilde. This is singleton X. Okay. Then notice that E tilde is a union of Ens. Can you quickly see this? Why do I write it X? This should be E tilde.
Yes, sir.
Yeah. So this is true because of whatever I have written above. But then this implies that at least one of the ENs is uncountable. I mean, sorry. But why would this imply that at least one of the ENs is uncountable? So here I am going to prove it by contradiction. Assume that E is uncountable. Or rather, assume that E tilde is uncountable. That is also sufficient for us. Okay. Now E tilde is uncountable. Therefore, this union is uncountable. And hence, one of the E tildes is uncountable. At least one EN is uncountable. But then, if En is uncountable, let us look at this family. And let us define it as x minus 1 over 2n, x plus 1 over 2n, such that x comes from En, where this, n I have now fixed. Are you following?
Yes, sir.
Okay. Now, okay, can you quickly tell me whether this is a family of disjoint intervals?
Yes, sir. Since X was an isolated point, then
Exactly.
with
Since
a shorter radius, yeah.
correct, correct. So let me just quickly give the proof. So if there is a z inside x minus 1 over 2n, x plus 1 over 2n, intersection with y minus 1 over 2n, y plus 1 over 2n for xy in En, this would imply mod of x minus y less than or equal to mod of x minus z plus mod of y minus z. But each of this is less than 1 over 2n, which is 1 over n, which implies that actually y is inside x minus 1 by n to x plus 1 by n. So this is possible exactly when y is equal to x. If y is not equal to x, this is not possible, right? So this is a family of disjoint intervals. And also, this is uncountable. Because for each x in En, we are getting an interval. So this f is uncountable. But this contradicts something, right? We just proved in the beginning of this session that we cannot have an uncountable family of disjoint open intervals. Yeah.
Yes, sir.
So therefore, these all these ENs must be countable. Therefore, E tilde is countable. Hence, E is countable. But once E is countable, this implies that E is a null set. Right? This is what we proved in the beginning of this assignment, right? Somewhere, I think the first question itself, or the second question.
Yes, sir.
Okay, fine. So this is about the fifth question. What about the sixth question? Sixth question asks that if E is uncountable, then E is not a null set. So is this true?
No, sir.
Why?
So because Cantor set is such an example.
Exactly. False, because Cantor set is uncountable, but not. Sorry, and a null set, right? And a null set. Okay. So this is sixth. Uh, Seventh question says that the set of irrational numbers is a null set. Again, is this true?
No, sir.
Why?
Using the countably subadditive property, uh,
Mm-hmm.
lambda star of R must be less than equal to lambda star of rational and
Exactly.
lambda star irrational.
Exactly. So why is this true? Because lambda of R, this is plus infinity. This must be less than or equal to lambda star of Q plus lambda star of Q complement. But this is anyway zero. This implies that lambda star of Q complement is actually plus infinity. It is not null. Okay. What about next question? So if I is an interval, then I is not a null set. What do you think about this?
No, sir.
Not true, right? Why? Yeah, why is this not true?
No, sir. Since interval a comma a is null set.
Exactly. So singleton x is an interval and a null set. The remaining questions were easy. Only the fifth question was a bit difficult. Okay. So if E is a null set, then E plus X is a null set. What do you think?
Yes, sir. So since we already shown that the outer measure is translation invariant.
Exactly. So it follows from the translation invariance. Okay. And the last question, that if E is a subset of R and there is a X in R such that X times E is a null set, then E is a null set. So again, what do you think?
So we can choose x equals to 0. So for a non-zero measure, we can still get this answer.
So if you look at lambda of 0 times R, this is 0, but R is not a null set. Okay. So any further questions from this assignment or anything that we have covered till now?
Sir, actually, this is I just had one question.
Mm-hmm.
Um, when we are defining the measurable sets, then we use this particular definition that lambda star of y is equal to lambda star of y intersection e plus lambda star of y intersection e complement.
Correct.
So, what is the so this seems very arbitrary to use such a definition. So, what is the motivation behind it?
It is not. It is not arbitrary. See, what we want to do. Say I want to uh, measure this set y. Okay. I don't know how to measure it because that original length function or whatever measure it is given on a very smaller class, right? And then we have extended it to the set of all subsets, but that requires taking some open cover, I mean, not open covers, taking some covers and then taking the infimum of something. But what natural things happen is that suppose that this is measurable. I mean, if I know the method to measure this, and if I take any other set E, then what should happen? This volume and this volume, they together should give us the volume of Y, right?
Yes, sir.
So what is this? What is this volume? This is Y intersection E. And what is the other volume? It is the Y intersection E complement.
Yes, sir.
Correct? So it is natural to expect that if I measure these two volumes, then the sum of them should be the measure of Y. So I am saying volumes because it sounds fancy. But when I say volume, it could be length, it could be area, or any other measure that is given to us.
Yes.
Natural to expect that lambda star Y is lambda star E, Y intersection E plus lambda star Y intersection E complement. And this should happen for any Y. If this is true, then we say that E is measurable, right? Yeah. Are you following? Is this fine?
Yes, sir.
Any other question?
Yes, so over here, so if we take any arbitrary y subset of x,
Mhm.
then we will be able to calculate the measure for y. Lambda star of y will be well defined.
Lambda star Y is anyway well defined. That is infimum of something, and that
Yeah.
something is bounded below by zero.
Oh, but now the problem arises when if you have say some collection of sets subsets of x such that the
Mhm.
countable additivity property is not satisfied, then we would say that that collection will not may not be from the set of measurable sets.
It won't because we require that countable additivity there.
Oh, so this kind of construction or this kind of definition will actually ensure the countable additivity. Is that because we are using this?
No, that is not because we are using this. I mean, this does play a role somewhere in between, but the major point is that lambda, which was earlier given to us on the algebra, that was countably additive.
Yes, sir.
So that plays a major part. And of course, this is a natural thing. If I break the whole space into two things, then the volume of the first thing plus volume of the second thing should give us the whole volume. So this is actually what I'm trying to say here is finite additivity, right?
Yeah, yes, sir.
But this is not exactly finite additivity because lambda star is not a measure. It is the outer measure. So I am writing it in quotations.
Yeah, this gives a hint of finite additivity. It still gives,
Correct. Correct.
but then
And
yeah,
then from the definition of lambda star, we can get countable sub additivity and other things. So yeah, this does play a role to get that countable additivity finally.
yes, sir. Okay, sir. Yeah,
Okay. So any other question?
no, sir.
Any other question from the online audience? Uh, okay, I think not. So, okay, let us stop here and we'll meet next Friday with the discussion on week 7. Thank you.
Thank you, sir.